today is part 1 on our video series of transforming functions. So in order to do this lesson today, you need to have a good grasp of how to graph the first 5 parent functions that we've already learned about, and also to understand what their domain and range are. So once we have these parent functions, we can make them change their shape and change their location depending on transformations that we apply. Stretches, compressions, reflections, and translations. So if our original function is f at x, then we can either apply an a, d, and a c. These are called parameters, okay? So in a normal function, a, d, and c will be numbers, and then f at x represents whatever the parent function is. That part's a bit confusing, but once you see some examples, I think you'll get it. So a is multiplied outside the original function. So it can be a vertical reflection, so reflect the function down across the x-axis if a is less than 0, so if it's negative. If the value is greater than 1, it stretches the function by a factor of a. So if a is 2, everything is 2 times as high. If a is 7, everything is 7 times as high or 7 times as low. If a is between 0 and 1, that's a vertical compression. So if a is a half, everything's half as high or half as low. If a is a third, it's a third as high, etc. Now our d value, which is always of the form x minus d, can either move left, okay, so if you have something like d plus 1, that's actually like that should be an x. That's like x plus 1, that's like x minus a negative 1, so you're going left. And if it's positive, so something like x minus 1, that would just be moving the whole function right 1. C is a vertical translation. So you're either moving everything up by a factor of c, if c is greater than 0, or down by a factor of c, if c is less than 0. Okay, so if our original function is a parabola, x squared, then a is applied outside the function, so outside the squared, and it's multiplied. The minus d part is inside the function, so inside the squaring, and c is added on the outside. So if we have our a value of 2, a d value of 3, and a c value of 1, then our function is 2 bracket x minus 3 squared plus 1. So everything is twice as high, moved right 3, and up 1. If our original function is a square root function, then again, the minus d is inside the parent function, so it would be underneath the square root. The a is multiplied outside of it, and then the c is added on the end. So that would look like, in this example, 2 times the square root of x minus 3, and then plus 1 is chilling outside here, outside of the square root. And if our original function was reciprocal, then a is multiplied outside, the minus d is underneath in the denominator because that's inside the function where x is, and then c is added on the outside. So that could look like this, 2 times 1 over x minus 3 plus 1, or you could choose to write it this way. You could put the 2 up here in the numerator, because 2 times 1 is just 2. So either way, this means a vertical stretch by 2, right 3, and up 1. And that's how you're changing the original reciprocal function in this case. And finally, the absolute value function. You put the 2 on the outside, the x minus 3 within the absolute value lines, and then plus 1 here on the outside. So if you're given an original function, and then given a generic changing like this, you'll know how to apply it to any of the parent functions. Finally, you should think about what all this means. So the shape of the graph depends on what parent function you're given. If it looks like a parabola or like a square root function. And then the value of a, so if it faces up or down, and the sign of a, so if it's tall and skinny or short and fat, that will be determined by a. So that's the original shape of your graph. Then once you have that shape, you're going to be moving it left or right, which is D, and then up or down, which is C. So that kind of tells you the location of the graph. The domain is affected by, well, you look at the original function and think, the parent function, and think about what's its domain, and then just move that domain left or right dependent on D. The range, you look at the original parent function, and then move it up or down depending on C, and then it could be flipped up or flipped down depending on A. So most people remember C, but sometimes forget about A. So if normally your range is greater than 0, greater than or equal to 0, and it's moved up 4, then that means it's greater than or equal to 4, unless A is negative, which could mean that it's less than or equal to 4. So you have to look at how C has changed the function, but also if A has flipped the function or not. It doesn't matter if it's been stretched or compressed, only if it's been reflected, if you're looking at how it affects the range. Finally, you have to be careful in the order in which you apply your transformation. Think about bed maths. You have to do the multiplication first. So the reflections and the stretches or compressions have to come before the translations. So just think RST is in alphabetical order. So in your homework and on the test and exam, you're going to be asked to take something like this, describe the transformations, sketch the new graph, and also give me the domain and range. So the first thing you always want to do is identify the parent function. In this case, it's root x, okay, because it's a square root. So this is just the square root function, and then it's been transformed. So take a grid paper, and draw your original function, f at x equals root x. You always start with your parent function. So I just start with the 4 key points, 0, 0, 1, 1, 4, 2, and 9, 3. So you always want to do at least 4, maybe up to 6 points, and then you're just transforming those points on the original parent function. Then you want to be able to describe what these translations do. So let's identify our parameters. So A is equal to negative a half. So this negative means that it's being, that it has a reflection on the x-axis. And this half means that it's a vertical compression by 1/2. So everything is half as tall or half as low as it originally was. Then our D value, be careful, is negative 3. Because normally it's x minus D, so x plus 3 means that it's really minus a negative 3. So that means that we're going to translate left 3. And then our C value is 4, so that means we're going to translate up 4. Okay, so now that we've described our parameters, we're going to sketch the new graph. So we're going to do it in 2 stages. First, we do our A value, and then we're going to do our D and our C values together. So we need to reflect everything down, and then also compress it by a half. So 0 compressed is just still 0, and reflected is still 0, so it stays the same. Okay, 1 is reflected down to negative 1, and then it's compressed by a half. So it's a half as low down as it used to be. Okay? Or you can do the compression first and then reflect. You can think about this is too high, so now a half of that is 1, and then it's reflected. Okay, it doesn't matter the order that you do that in. And this is 3 high, so then we reflect down to negative 3, and then a half of negative 3 is negative 3 over 2, or minus 1.5. So this is the function minus a half root x. It only has the A in it because that's all we've applied so far. So now we want to apply the D and the C together. So we look at, this is the shape of our graph, and now we just move it to its new location. So we move everything left 3 and up 4. So you take your 0, 0 and move it left 3 and up 4. Okay, this one left 3, up 4. Left 3, up 4. And finally left 3, up 4. So I think with a square root function, having 4 points is enough to show the shape. So notice that it's kind of fatter than the original because it's been compressed, and it also starts to the left and up because it's been moved left and up. So that's our sketch. So to make sure it's right, I like to label some points. So this is -3, 4. This is -2, 3.5. This is 1, 3. This is 1, 2, 3, 4, 5, 6. And this is 6, 2.5. So we want to take those x values, run them through the transform function, and make sure they spit out the right y value. So if our points are right, then we did it right. Then we can pat ourselves on the back. We can feel more relaxed when we hand in that test. So let's take 1, 3. So let's put 1 in the function. So 1 plus 3 is 4. The square root of 4 is 2. Minus a half times 2 is -1. Minus 1 plus 4 is 3. Yay, we did it. When we put in 1, we get out 3. Pause the video now and put in 6. Make sure you get out 2.5. And then put in -2 and make sure you get out 3.5. Okay, the last thing you're going to be asked to do then is to describe the domain and range. So remember, domain is just what x can be. So take a look at this. You can think about the function as starting over here at the x value of -3 and then going in this direction. So x is greater than or equal to -3 and then any real number within that restriction. Range, remember we're thinking where can it go up or down? It's our y value. So we start at 4, the y value of 4, and then it all goes down from there. So our y's such that y is less than or equal to 4, and then any real number. So remember, domain, think left and right, and range, think up and down. Okay, so now we're going to do a reciprocal example. So something that's different, what I did differently here, is that I just gave you the generic equation of this transform function, and I'm telling you now to apply it to 1 over x. So if this happens, then the first thing you want to do is rewrite the function in its reciprocal form, so you don't get confused. So g at x is equal to, so think about it, 1 over x is the original function, the parent function, so the 2 is multiplied outside, then 1 over x minus 1, and then the -3 is on the outside. If you're confused about this, then rewind the video and look at that chart and see how we come about this. Okay, so now let's identify all of our parameters. So our a is equal to 2, so that means that we have a vertical, think, is it a stretch or compression? Well, it's greater than 1, so it's a stretch. Stretch by 2. Okay, there's no reflection because it's positive. If it was negative, there would be a reflection, but it's not, so we don't have to worry about that. Now, d is equal to, think about it, is it 1 or -1? It's 1. Okay, so that means that we're going to translate right 1. And our c is -3, so that means we're going to translate down 3. Okay, so that's describing the translations. Now we need to actually sketch the function. So we have our 6 key points in a reciprocal function. 1, 1, a half, 2, and 2, a half, and then the same ones, but just the negative versions. So first we're going to apply the vertical stretch. So everything is twice as high as it currently is. So instead of being 2 high, it's now 4 high. Instead of 1, it's 2. Instead of a half, it's 1. Okay, and the same thing goes for the negative, it's just how low it is. Okay, so the asymptotes haven't changed or anything, just it's been stretched by 2. So it's like grabbing these and stretching them by 2, if you can visualize that. So now we're going to take this graph and just move it. So we're going to take the pink one and take the whole thing right 1 and down 3. So it's easiest to just do that point by point. But what else that is unique to a reciprocal function is that we have these asymptotes. So I'm going to go ahead and move the asymptotes. This one is being moved right 1. Okay, because that is, so this is x equals 1. And this one is being moved down 3. Yes, 3. So really you should use a ruler when you do this, but just for time I'm not going to. So this is y equals -3. So those are your new asymptotes. So you know that the shape should be kind of around those asymptotes. Okay, so I'm going to take the pink one and move everything right 1 and down 3. So right 1 and down 3. Right 1 and down 3. Right 1 and down 3. You should notice how you can kind of draw this along with the asymptote, because you have to show the behavior of the function approaching that asymptote. Okay? Then you do the same thing with this left side of the function. So over 1 and down 3. Just have to kind of eyeball that one. Over 1 and down 3. Over 1 and down 3. Sorry. Yes, no, sorry. Okay, so there. Ooh, I do that a little bit sloppy. Just really look more like this. There we go. Approach the asymptote. There's our function. So let's plot some points. 1, 2, 3. So this is 3, -2. 2, -1. And 1.5, 1. And you can do the same thing to plot the points for these down here. So you want to make sure, again, you want to run these through your function and make sure that they're right. So put 2 inside the function. You get 1 over 2 minus 1, so 1 over 1, which is 1. 2 times 1 is 2. 2 minus 3 is -1. Yay, it's right. So now do the same thing for the x values of 1.5 and 3. Make sure you get the corresponding y values. You can also do it for this part of the function down here. So now we have to do our domain and range. So for the domain of a reciprocal function, really you just need to look at the asymptotes. So whatever the asymptotes are, that's what your x value and your y value can't be. So your x value cannot be equal to your vertical asymptote of 1. Why? Well, if you put 1 into the function, you would get a 0 in the denominator, and you can't divide by 0. So you can put anything into this function except for 1, because that would break the whole function, because that would make you divide by 0. So your range then is whatever your horizontal asymptote is. So in this case, y cannot equal -3. Well, you might be asking, why can't y equal -3? Well, think about it. If this part of the function can never be 0, then the whole function can never be -3, because you'll never have 0 minus 3. So that's the first part of transforming functions. One thing I did want to mention that is a common mistake with students. You'll notice that when I did my scale, everything was 1-to-1 scale. So each little tick mark here represented 1, going left or right and going up or down. So something you might do sometimes is change your scale. So you might have your scale going up by 2, like 2, 4, 6, 8. So you have to be careful. If you have to move right 1, you don't move a whole tick if your scale is 2. You'd only be moving half a box. So be very careful if you do not use a 1-to-1 scale that you're moving left or right appropriately depending on what your scale is. That's a big mistake I see quite often. So thanks for for watching, and I hope you learned lots.